Hello and welcome to this lecture on advanced electric drives. In the last lecture we are discussing about the multi-level inverters and how they can be used for drives application. The multi-level inverters can give us more than 2 level of voltages. Usually in a 2 level inverter we get 2 levels of voltage, either 0 or VDC. In a multi-level inverter we can get more than 2 level. It could be 3 level, it could be 4 level, 5 level and so on. So, we have already seen that multi-level inverters can be broadly classified into 3 different categories, and they are the diode clamp multi-level inverter, the flying capacitor multi-level inverter and the cascaded H-bridge multi-level inverter. So, these are the 3 categories that we were discussing in the last lecture: the diode clamp multi-level inverter or DC MLI, or the flying capacitor multi-level inverter FC MLIs, and H-bridge multi-level inverter or HB MLI. So, in the last lecture we have already discussed number 1 and number 2, that is, we have already discussed the diode clamp multi-level inverter structure, and also we have discussed about the flying capacitor multi-level inverter. Now, let us look at the H-bridge multi-level inverter. That is, the third category is H-bridge multi-level inverter. Now, let us look at this topology of H-bridge multi-level inverter. So, this is called cascaded H-bridge multi-level inverter, or we can just say this as HB, H-bridge multi-level inverter, H-bridge MLI. Now, in this case what we have so many H-bridge inverter connected in cascade, so that we can add or subtract the various voltages to get more than 1 level, more than 2 levels and so on. So, let us take an example when 2 H-bridge inverters are connected in cascade series. So, we have 2 single phase H-bridge inverter connected in series, and what are the possible outputs that we have? So, we have the construction like this. This is basically the DC capacitor that we have, and then we have the IGBT inverter. It is a single phase inverter that we have here. And they are all IGBTs. We have the anti-parallel diode, the feedback diodes here, and then we have the second, and this is VDC. The DC voltage is here is VDC. Similarly, we have a second inverter also having the same DC voltage VDC, and this is again one H-bridge inverter. So, this is the H-bridge inverter that we have, the second H-bridge inverter. these IGBT switches, and this is the output. Let us say this is for phase A, so we can call this to be phase A, and this point is connected to the second bridge in the following fashion. And this is, let us say, one phase, we can have the neutral here. So, this is the neutral. So, let us say this is basically the two edge bridge inverter connected in cascade, and each one having a decoupling voltage of VDC plus VDC, and this is for a single phase. Usually we have a three phase drive, so we can have phase A, phase B and phase C. The similar construction will repeat for phase B and C. Now, if we have the structure like this, what are the possible output voltages that we can have? So, this VDC and VDC can add. So, if we add this VDC and VDC, we get 2 VDC. So, we have the first possibility that we can have 2 VDC, and let us say we have VO1, this is plus minus, and this is VO2, this is plus minus. So, for 2 VDC we can obtain this 2 VDC provided VO1 will give us plus VDC and VO2 will also give us plus VDC. And then if the two voltages are VDC and VDC, what we have VAN. VAN is VDC plus VDC, that is 2 VDC. So, we have VAN here. The output voltage is equal to VO1 plus VO2. So, this we are writing in this case VAN. So, VAN is 2 VDC provided VO1 is VDC and VO2 is VDC. Now, let us say that out of this VO1 and VO2, one of the voltages is 0. It is possible, because in a inverter we can make the output voltage 0 by short circuiting the output. So, if VO1 or VO2 is equal to 0, we get just VDC. So, we can have here that is equal to VDC provided VO1 is equal to VDC and VO2 is equal to 0, or VO1 is equal to 0 and VO2 is equal to VDC. This is also possible. So, if one of the voltages is 0 and other voltage is VDC, the output is going to be VDC. And then we can have a situation where both VO1 and VO2 both are 0. If both are 0, the output VAN is equal to 0. So, we can have that possibility also, that is equal to 0, and this is true when VO1 is equal to VO2 is equal to 0. Okay? And then let us talk about the negative polarity. VO1 can be negative. So, if VO1 is minus VDC, VO2 is 0, or VO1 is 0 and VO2 is minus VDC, output is minus VDC. So, that is also one of the possibility we have. So, we can have that is equal to minus VDC provided VO1 is minus VDC. In an inverter, we can easily invert or easily reverse the output voltage, that is possible. So, VO1 is minus VDC and VO2 is 0, or VO1 is 0 and VO2 is minus VDC. So, this is one situation. And then we have the fifth one is that VAN could be minus 2 VDC, and that is possible when VO1 is minus VDC and VO2 is minus VDC. So, we can have that is equal to minus VDC, minus 2 VDC, and this is true when VO1 is minus VDC and VO2 is also minus VDC. So, how many labels we have? We have in fact 2 VDC, VDC, 0, minus VDC and minus 2 VDC. So, this configuration is able to give us 5 different voltage levels. So, with 2 cascaded inverters, edge bridge inverters, we can get 5 level of voltage. So, it is basically a 5 level inverter. So, the formula is this, that if the number of bridges cascaded is n, we can have 2n plus 1 number of levels. So, number of levels here, number of voltage levels is equal to 2n plus 1, where n is the number of edge bridges cascaded. Now, this is actually also employed in many drive system, but the main problem is this, that whenever we have such kind of inverters, we need to have independent DC voltages. In fact, for this situation we would have, or we would require 2 VDCs. So, if you have 3 levels or 3 inverters, edge bridge inverters, you would require 3 VDCs. So, these are the voltage sources that we need. So, we need independent source here. This will be isolated from this. There should not be any connection between one voltage source with the other voltage source. That is not possible. That should be avoided. So, here we have 2 independent voltage sources. Then if you have one more bridge in cascade, we need 3 independent voltage sources, and in general we would require n independent voltage sources. So, sometimes having independent sources is a problem. So, although this is also employed in drive, it is not as popular as the diode clamp multi-level inverter, where we have 3 different levels. We can have multiple levels also, but we can supply from a single voltage source. So, this is an example of a multi-level inverter, where we can get multiple levels by cascading various edge bridges. Now, out of these 3, the diode clamp multi-level inverter, the flying capacitor multi-level inverter and edge bridge multi-level inverter, we would select one of these inverters and go ahead with the drive implementation. The objective is to have high power drive. So, we will choose out of these 3 the diode clamp multi-level inverter for drive implementation. So, let us have a look at a 3-phase, 3-level diode clamp multi-level inverter. So, we are taking actually a 3-phase, 3-level diode clamp multi-level inverter. And let us first see the structure of this inverter. So, we have 3 different phases. So, let us first draw this complete inverter. So, we have the DC link in this case, and there are 2 capacitors here, one capacitor and the other capacitor. And then what we have here is that we have 4 devices per phase, this is one leg, second leg, this could be for phase B, and then we have the third leg here. So, each leg has got 4 IGBTs, and each IGBT will have its anti-parallel diode. Similarly, here also, this is for phase A we are drawing. Similarly, for phase B we have the IGBTs here, this for phase B. And then we have for phase C, and we can also name them accordingly. This is SA1, this is SA2, this is SA3, this is SA4. Similarly, we have SB1, SB2, SB3 and SB4, SC1, SC2, SC3 and SC4, and we have the outputs, and the outputs can be taken from this. These are the outputs we have. This is for phase A, phase B and phase C. We can have a load which will be connected to A, B and C. Now, this is actually the main inverter, but we also have the clamping diodes. That is why we call this to be a diode clamped multi-level inverter. So, this is diode clamped multi-level inverter. So, what are the clamping diodes? The clamping diodes are here. So, we have the clamping diodes which are present here. This is one diode, and this diode, we have the other diode here, and these two are connected to the midpoint of the battery, which is basically two capacitors here, and if this is VDC plus minus, so what we have here is plus minus and plus minus. So, we have almost equal distribution of voltage. So, VDC by 2 and VDC by 2 here. Now, similarly for phase B, we have two diodes here, clamping diodes, and this is for the upper switch and we have the lower switch here, and these two are connected together, and then this is connected to the midpoint of the capacitor in the following fashion. For phase C also we have two clamping diodes, and this is for the upper bridge, the same leg, the upper two IGBTs. Then we have the clamping diode for the load switches, and these two are connected together, and then this midpoint of this is connected to the midpoint of the capacitor. So, these clamping diodes help to get the 0 level. So, we have to, each phase can give us 3 independent labels. Each phase can give us plus VDC by 2, minus VDC by 2 and 0. In fact, this we have already discussed in the last lecture, that in a diode clamp multi-level inverter, we have 3 different labels for 3 level inverters. It is plus VDC by 2, minus VDC by 2 and 0. Let us concentrate on phase A. In phase A, we have switches SA1, SA2, SA3 and SA4. Now, when we turn on SA1 and SA2, when we switch on these two switches, the voltage VA, we can call this to be the neutral point N. This point we can call the neutral point here. VAN will be plus VDC by 2. So, if we write down the voltages VAN here, it could be plus VDC by 2 when we switch on SA1 and SA2, and then it could be 0 when we switch on SA2 and SA3. So, when we switch on SA2 and SA3, the voltage output is 0, VAN is 0. So, if we switch on SA2 and SA3, what happens here? We are having a clamping diode. This is basically the point here which is connected to this. So, if the current is positive here, the positive current will flow through this diode and this IGBT SA2 and will go here. Positive current means the current is coming out of this. We can call this to be IA, the direction of positive current. Similarly, for phase B, we can say this is IB, the direction of the positive current, and for phase C we have IC, the direction of the positive current coming out of this inverter. So, if we turn on SA2 and SA3, this point A is clamped to the neutral point, and the neutral point is having 0 voltage. So, this diode and this IGBT will be connecting this A to the neutral point if the current is positive. If the current is negative, it means the current is going into this inverter. So, SA3 will be carrying this current, because SA3 has been applied a triggering pulse. So, SA3 will be conducting, will carry current through this diode. This will be connecting to the point N. So, we can, in fact, we can call this to be the clamping diode DAC1 and DAC2, the clamping diode 2. Similarly, we can call this to be DBC, phase B clamping diode 1, and this is DBC2, the clamping diode 2 for phase C. Similarly, this is the clamping diode for phase C, upper diode, and DCC2, the lower diode. So, the clamping diode helps connect that point to the neutral point or N of the power supply, and hence we can have a 0 voltage. Now, if we switch on, let us say that we switch on SA3 and SA4. Now, if we switch on SA3 and SA4, clearly AN, this voltage A with respect to the neutral point would be minus VDC by 2. So, we can say here that VAN is equal to minus VDC by 2 if we switch on SA3 and SA4. The same thing is true, similar thing will be true for phase B, and similarly we can have the similar thing for phase C. So, in fact, for every phase we can have 3 different labels, and hence when we connect a drive, the load in this case could be an induction motor. So, in this case we can have a load here, and this load could be an induction motor. So, we can supply this from the 3 phases of the inverter, and with proper control this motor can be made to respond to a given speed or given torque. So, we can have a closed loop torque control, or we can have a closed loop speed control. So, when we apply this to an induction motor, we can have lot of possibility. We have in fact here 12 switches, so 4 in each leg, SA1, SA2, SA3 and SA4. So, per phase we have 4 IGBTs, and for 3 phases we have 12 IGBTs. So, what we do here is that when all the phases will be switched, we get some space vector. And how many space vectors we have? Space voltage vectors. As we have the voltage vectors in a 2-level inverter, similarly we can have the voltage vectors in a 3-level inverter. So, each phase has got 3 possibility. So, we can show this by, this is called plus, positive voltage, this is called 0 voltage, and this is minus is a negative voltage. So, in fact, for phase A we have plus 0 minus. Similarly, for phase B also we can have plus 0 minus, these are the various status. Phase C also we have plus 0 and minus. So, if we analyze this, we get some space vectors, and the space vectors can be represented in the space as follows. So, we are drawing here space voltage vectors. So, we start with, let us say V1. Now, what is this V1? V1 is the meaning of this V1. So, we can call this to be V1F, the full voltage vector. Here we have plus, minus and minus. So, this plus, minus and minus correspond to, this plus correspond to phase A, minus correspond to phase B, and this correspond to phase C. So, we show it in the same phase sequence, plus, minus, minus. So, when we apply plus, minus, minus, the voltage vector is in this direction. So, it means the machine has got 3 different phases. In this case, phase A, and again we have phase B in this case. So, this is phase A, and this could be phase B, this could be phase C. So, when we apply plus, minus, minus, so basically phase is applied with plus VDC by 2, and phase B is applied with minus VDC by 2, and phase C is applied with minus VDC by 2, plus, minus, minus. So, this will be creating a vector which is equivalent to a vector in this direction. And then we go one step forward, we can draw another vector, that is V2. V2 is 60 degree ahead. So, we can call this to be V2F. Similarly, we can have another vector here that is 60 degree from this. So, this is V3f, and we have another vector we have V4f, this is V5f, and this is V6f. Now, when we write f means full vector, and then what is this? So, V3f is minus plus minus, and V5f is minus minus plus. So, V2f would be plus plus minus, V4f would be minus plus plus, V6f would be plus minus plus. Basically, the vectors which are diagonally opposite are opposite to each other. So, for example, V1f and V4f are opposite vectors. So, if V1f is plus minus minus, V4f is minus plus plus. So, we can construct these voltages, these vectors, and these vectors would represent the, if you join the tip of these voltage vectors, what we obtain is a regular hexagon, as we have obtained in case of a 2-level inverter. So, if we join the tips of these voltage vectors, we get a regular hexagon as we have obtained in case of a 2-level inverter. Now, we have some more vectors also. Now, we can also apply half voltage vector. Half means the voltage is half here. So, we have the full voltage vector V1f. What about V1h? So, we have another voltage vector called V1h, just exactly half, but the direction is the same. The direction being the same, we can get here V1h, and what are the various status in this case? The status could be in this case plus 0 0, or it could be 0 minus minus. So, we have two possibilities, 0 minus minus and plus 0 0. Imagine the situation where we have replaced this by 0 1 0 here, the 0 voltage here and 0 voltage here. Earlier we had minus VDC by 2, and instead of applying minus VDC by 2 to phase B and phase C, we apply 0 voltage vector or 0 status there. So, when we apply 0 voltage to phase B and C, the amplitude of the vector is half. The direction is the same. We have plus 0 and 0. The direction is still in this direction, but the amplitude is half, because instead of applying minus VDC by 2, we have applied a 0 here. The voltage is reduced. So, if the voltage is reduced, the amplitude is reduced, however, the direction will be the same. There is one more possibility. We can have the same voltage vector by having 0 in phase A. So, we can have another possibility that you apply 0 in phase A, but apply minus VDC here and minus VDC by 2 here. So, in this case also the effective vector is minus VDC by 2. So, it is again minus VDC by 2. So, again it is half. So, we have two possibilities. It means the half voltage vector can be obtained by two possible combinations. For example, V1h can be obtained by plus 0 0 or 0 minus minus, that is possible. And similarly, we can have half for V2 also. So, this is V2H, and this is possible by applying plus 0 or 0 minus. So, we have two possibility, and similarly we can have half for V3. So, we can call this to be V3H, and that is possible by applying 0 plus 0, or we can have minus 0 minus, that is also possible. And we can have V4H, V4H is somewhere here, half of V4F. So, it is V4H, the half voltage vector, and that can be obtained by applying 0 plus plus, or we can have minus 0 0. Similarly, we can have a half voltage vector here, V5H, and that is possible by applying minus 0 or 0 plus, and we can have the sixth half voltage vector here, half of that. So, this is V6H, and that is possible by applying plus 0 plus or 0 minus 0. So, these are the half voltage vectors. So, do we have any other voltage vectors? Because we have to find all possible combinations which are relevant here. Now, we have intermediate voltage vectors. It means in between V1F and V2F we have one V1I, and that is called an intermediate voltage vector. So, that is shown in the following fashion. So, we have the voltage vector which is in between this, and this is called V1I, the intermediate voltage vector, and this is possible by having plus 0 minus. So, it is in between V1F and V2F. Similarly, we can have an intermediate voltage vector here, and that is V3I, V2I. So, we have V2I here, and similarly we can have one vector here, that is V3I. We have one intermediate voltage vector here, that is V4I, and this is V5I, and we have again another voltage vector here, that is V6I. So, we have the intermediate voltage vectors as well. So, we have 6 intermediate voltage vectors, and they are basically in between two full voltage vectors. Say for example, in between 2 and 3, V2F and V3F, we have V2I. So, when we switch from V2F to V3F, we have plus plus minus to minus plus minus. So, the intermediate state is 0 plus minus. So, we have to go through this state to reach to V3F. Similarly, when we switch from V3F to V4F, we change from minus plus minus to minus plus plus, and hence the intermediate vector here is minus 0 minus plus and 0. So, what we have here is minus plus and 0. Similarly, from V4F to V5F, we go from minus plus plus to minus minus plus, and the intermediate voltage vector V4I is minus 0 plus. Similarly, V5I is in between V5F and V6F. So, and that is basically 0 minus plus, and V6I is between V6F and V1F, and that is plus minus 0. So, these are the 6 intermediate voltage vectors. We have also, apart from this, we have also 3 zero voltage vectors. The zero voltage vectors does not have any magnitude and also has got no direction, and these are applied when we have the short circuiting of the 3 phases. If we short A, B and C, we essentially obtain a zero voltage vector, and that means these all 3 phases should be connected to either plus or minus or 0, and the zero voltage vectors are located at the center of the hexagon. So, we have in fact Vz, and Vz is located at the center. This is Vz, and this Vz is obtained by either by plus 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 or minus 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 or 0 0 0. So, we have 3 different possibility. So, if we apply plus 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 or minus 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 or 0 0 0, that will result in 0 voltage vector. So, how many possible voltage vectors we have here? So, we have in fact, if we list here full voltage vectors, so we have full voltage vectors or full vectors. How many full vectors we have? We have 6 full vectors, and then we have half vectors. The amplitude is half. So, we have 1h. For 1h we have 2 different combinations, 1h to 6h, and for each one we have 2 different combinations. So, we have in fact 12 half vectors. So, we have 12 half vectors. Then intermediate vector, we have 6 intermediate vectors, and we have in fact the 0 vectors, we have 3 0 vectors. So, if we add these 4 possible vectors, the full voltage vectors, the half voltage vectors, the intermediate voltage vectors and 0 voltage vectors, we get in total 27 voltage vectors. So, in fact, in a 3-level 3-phase diode clamped modulable inverter, we have 27 voltage vectors, out of which 3 are 0 voltage vectors. So, the total number of voltage vectors here is 27. So, when we feed induction motor from this multi-level inverter, we have in fact lot of possibility. It means we have lot of flexibility in control, and hence we have better control of torque. Maybe the torque ripple is reduced here. In 2-level inverter, we just had 8 voltage vectors, 6 are non-zero voltage vectors and 2 are 0 voltage vectors, as opposed to a 2-level voltage source inverter. In a 3-level diode clamp multi-level inverter, we have 27 voltage vectors, and hence we have more flexibility. So, we will be discussing about a direct torque controlled induction motor drive fed from a 3-level diode clamped multi-level inverter. Direct torque control, this is also called DTC, of an induction motor fed from a 3-phase 3-level diode clamped multi-level inverter, DCMLI. So, what we have is the following. We have the inverter structure, and then the inverter is feeding an induction motor, and we have 27 voltage vectors. Now, if we go back to our previous diagram, in this case we can divide this space into 6 sectors. So, what we have here is the following, that we have 6 sectors here. We divide the complete region into 6 sectors, and each sector is 60 degree. So, this is one sector 60 degree. So, this is sector 1, this one is sector 2, and each one is 60 degree. The spread is 60 degree. We have sector 3 here, sector 4, sector 5, and sector 6. So, we have 6 different sectors, and depending upon the sector in which we have the flux vector, we can choose the corresponding voltage vector. We have already seen the control aspect of a 2-level inverter fed director control of induction motor. There is some similarity between the director control with 2-level inverter and that with 3-level inverter, but in a 3-level inverter we have more flexibility because we have more number of voltage vectors. So, let us recapitulate some of the equations that we derived for a 2-level inverter fed director controlled induction motor drive. So, we will just recapitulate a few equations. So, first of all, we understand that the torque is basically the product of flux and current psi ds IQS minus psi QS IDS, and this can be simplified in the following fashion, that is equal to 3 by 2 into P by 2 Lm by sigma Ls Lr psi s amplitude and psi r amplitude and the sine of the angle between them. So, this basically is a very fundamental torque equation which will help us understand the director control of induction motor. Now, here the torque is proportional to the amplitude of the stator flux, amplitude of the rotor flux, that is psi r, and the sine of the angle between them. So, in fact, what we have here is the following. We have psi s, the stator flux linkage, it is a vector, and then we have psi r is the rotor flux linkage, it is also a vector, and the angle between them is gamma SR. So, we have the d axis and the q axis, the stationary d axis and the q axis, and these are the rotating flux. The fluxes are rotating at a speed of the synchronous speed omega e. So, both psi s and psi r are rotating at omega e, the synchronous speed, and the angle between this is constant in the steady state condition, and the angle between psi s and psi r is gamma SR. Now, when we want to control the torque, we have two possibilities. Either we can control psi s or we can control the angle between them. So, we can control the torque by controlling the flux or controlling the angle between the two fluxes. psi s can be controlled directly. We do not have any hold over psi r, the rotor flux. The rotor flux is induced from the stator side. So, this we cannot control. We can only control psi s. So, how do we control psi s? So, we can control psi s by this following equation. So, delta psi s vector is equal to, basically what we have, we can take the voltage minus the resistance drop ISRS into delta t, and that is equal to ES, the induced EMF, into delta t. So, basically the flux can be changed by changing the induced EMF. If you apply a voltage, there will be some induced EMF, and the induced EMF will change the flux. And if we ignore the resistance drop, the induced EMF is approximately same as the applied voltage. So, if we ignore the resistance drop in this case, so we can assume that this is 0. So, if we do that, what we obtain here is that is approximately equal to Vs into delta t. So, it is basically a vector equation. It means the incremental change in the flux linkage, delta psi s is the change in the flux. Suppose I have the original flux in this direction, that is psi s, and I want to change psi s by some amount. So, I will apply a voltage vector which is Vs, this is the Vs, and the Vs is applied for a time that is delta t, and that is equal to delta psi s, it is also a vector. So, when we have two vectors, we can find out the resultant of these two by completing the triangle. So, here we can find out the change of the flux is delta psi s, the resultant in this case this psi s is psi s not the initial value, the final value is psi s, and hence we can achieve the change both in amplitude and angle by applying a voltage vector. So, this is a principle, and we have to apply this Vs, and Vs is one of the 27 voltage vector that we have. So, so we have got 6 different sectors as we have already seen, and the sector information is obtained by tracking this psi s. We are basically controlling the stator flux. The stator flux is controlled. The stator flux vector can be in any one of the 6 sectors. So, normally we can find out the sector by finding out the angle of the stator flux vector with respect to the d axis. So, we have this flux in this case. So, we can define this angle in this case to be theta s, and theta s can be obtained in the following fashion. So, we can resolve this into two components, the d axis and the q axis component. So, we have one component in the d axis, we can call that to be psi ds, and the other component in the q axis we can call that to be psi qs. And how do we find out psi ds and psi qs? Psi ds and psi qs are found by the corresponding voltages. So, in fact, we can say here that psi ds is equal to integral of Vds minus ISRS dt IDS RS dt. So, we know the voltage in the d axis, we know the currents IDS, so we can find out psi ds. Similarly, psi qs is obtained by integrating VQS minus IQS RS dt. So, the applied voltages are known, VDS and VQS are known. So, we can find out psi ds and psi qs, and theta s is equal to tan inverse of psi q s by psi d s, and once you know theta s, we can find out the sector information about the flux. And the total flux in this case can also be calculated. Psi s amplitude is equal to under root of psi d s square plus psi q s square. So, these computations have to be done in real time to obtain the amplitude of the flux, that is psi s, and also the angle, that is theta s, from which we can obtain the sector information. So, this is the control principle of induction motor with direct torque control. Now, when it is fed from a multi-level inverter, we have lot of possibilities. In fact, we have 27 voltage vectors, and how we can appropriately apply these voltage vectors to control the torque and flux effectively, and this will be discussing in the next lecture.